Independence is an idea of the relationship between two events, and later we'll extend that to the relationship between two variables. But I need to know whether or not the probability of one event changes based on my knowledge of the occurrence of the other event. And so here we have a two-way table that shows handedness, either right handedness or left handedness, by gender. And we want to be able to determine whether or not two events are independent. Now, we're going to look at this from the viewpoint of conditional probability. If there really is independence between gender and handedness, then what we will see is comparable, as a matter of fact, equal probabilities as we work within this table. So let's just assume that we were looking at male students. First, we want to check the probability that we are left-handed knowing that we are male. So assume that we're asking whether or not being left-handed and being male are independent. So suppose we know that the person we've chosen randomly is male. There are 23 males, and of them, 3 of them are left-handed. So here's what we have. The probability of being left-handed, given I know I have chosen a male person, is 3 left-handed people out of 23 total. But if we use that conditional probability formula, we're looking at the probability of being male and left-handed divided by the probability of just being a male. Male is the condition. Notice that whatever the condition is, that's your out of in your probability. So this is 3 left-handed males out of 23 males. If I compare that to the unconditional probability of just being left-handed, not considering gender at all, then there are 7 left-handed people out of 50 people. So that probability is 7 out of 50. We need to know whether or not these two probabilities are equal. So we can change those to decimals. And here's what we'll find. The probability of being left-handed, given that we have a male person, is 0.1304. And the probability of being left-handed, despite gender or regardless of gender, is 0.14. And although these two probabilities are close, they are not the same. They have to be exactly the same probabilities, not rounded, not truncated, exactly the same. And so we will see here that these two are not independent. And here's why. The probability of being left-handed, knowing that I'm a male, does not equal the probability of being left-handed, which tells me that this condition has some effect on the probability of being left-handed. Therefore, these are dependent events. In general, in order for events to be independent, the probability of B given A has to be equal to the probability of B. In other words, A's occurrence has no effect on the occurrence of B. And this is why we have our general probability rule becoming more specific, or excuse me, our general multiplication rule becoming more specific for for independent events. Let me say that again. The general multiplication rule becomes more specific for independent events. The general multiplication rule says that the probability of A intersects B equals the probability of A times the probability of B given A. That's general. But I get a very specific rule for independent events. Because the probability of B will equal the probability of B given A for independent events, then I can change this to read the probability of A intersects B equals the probability of A times the probability of B. And again, this is only for independent events. And that's why at the top, we can check for independence just by using this idea. Hopefully this added some clarity. As always, if you have questions, feel free to ask.